can we do unsupervised learning with neural networks. And I looked at the, let's say, maybe one of the simplest realization or implementation of unsupervised learning, which is principal component analysis. And we talk about a null model and the what I call the retarding learning phase transition in this problem. So I will go back through the slides. I will go through the slides in a couple of minutes so that you have a more precise reminder. And it was also about the dynamical aspects, how to implement in a neural way the search for the top component with Oja's learning rule. And I started to talk about statistical mechanics of learning and did some calculation on the blackboard, but that was maybe a little bit too fast, so I will come back to that and explain to you what we find. Okay, so just as a reminder to be a little bit more precise, so what is the statistical framework here, or probabilistic framework? So we have a problem in n dimension. So n is supposed to be a large number, but you will see application. I will show you also some practical application to biological data where n is actually just a few tenths. But here the theory is in principle when n goes to infinity. And so we have vectors xi in n dimensions, in the n-dimensional space. And we're supposed here, I mean, we assume here that they are drawn from this multivariate Gaussian distribution, where tau is called the precision matrix. And the interesting case, obviously, is when tau is a non-diagonal, let's say, it's different from the identity matrix. So we get some effective coupling between the different components of the vector xi. So tau, this precision matrix, is the n by n matrix. And what we do here, we draw randomly p samples, which are independent realization from this multivariate Gaussian distribution. And the question we ask is it possible, when tau is different from the identity matrix, to find actually the interesting direction, that means the directions in the n-dimensional space corresponding to eigenvalues different from 1. So in the simplest setting, we assume the tau matrix has all eigenvalues equal to 1 but one eigenvalue, which is a little bit smaller than 1. So it's 1 minus s over 1 plus s, where s is a positive parameter. That means that the covariance matrix, which is the inverse of tau, will have one eigenvalue larger than unity. And if I draw randomly my p samples in the space, they will basically define a cloud of points. And this cloud will be larger and more extended in one direction, which corresponds to this specific symmetry breaking direction E here. And principal component analysis is basically the idea of projecting onto a very low dimensional space where you get more spread than along the other direction. So, okay, so now the question is, how can we get E, this direction, from the data? And if we do Bayesian inference, so these are the formulas I showed last week. Essentially, what we have to do is to build from the data the empirical covariance matrix, which is just the sum over all samples. So it's sum over mu here. Sorry, there is a mistake. Sum over mu xi j mu. And then we need to diagonalize this and find the top component. And the question is whether the top component of this empirical covariance matrix is actually aligned along the true direction, E, which was used to generate the data. And there is a well-known, so this is a well-known random matrix problem, which was solved a long time ago. And actually, in different settings. So this paper by Baik Benahous Péché in 2005 contains a proof, but actually the problem was known from the 70s at least. So essentially, there are two regimes, depending on the level of noise in the system. So how do we characterize noise here from a quantitative point of view? This is the ratio of the size of the problem divided by the number of samples, R. So if this ratio is very small, that means that you get a lot of samples. And very small means here smaller than s squared. Remember what s is. It's the difference between the top eigenvalue and 1. Okay? Then we are in a good situation, and one eigenvalue will come out from the spectrum here of noisy eigenvalues. And the corresponding eigenvector will have a finite overlap when n goes to infinity with the true E, the ground truth direction, with a value here which is the overlap squared here is given by this formula. So that means, so for instance, this is just an example. For s equal to 0.2, the critical value of R is s squared. As you decrease R, that means you get more and more samples. If you are above this threshold, the top eigenvector of the empirical covariance matrix is uncorrelated with the true E. If you are below, then you see a correlation. That is, the vector gets more and more aligned along the true direction, and you get perfect alignment when you have an infinite number of samples. Okay, so this is what we discussed. So what I wanted to show you is how to find back these results with a much more general setting coming from statistical mechanics. And I started with that last week, but I didn't have time to finish. So I will just briefly sketch the different steps we did and show you the schematically the different results. Okay, so let me just remind you here. Okay, so yeah, so the setting. So I use slightly different notation from this from the slide here, because I will use the notation from the paper by Ryman and Vandenbroek from 1996. So I think it's a phys-red E paper. So if you want to see more details about the calculation and the result, please go and look at the papers. I just sketched the main steps here. So they had a symmetry breaking direction, which I call E here, but in the paper this is called B, like breaking. So this is one particular let's say one particular vector in the n-dimensional space, and B is normalized to n. Let's say B squared is equal to n. So the norm of B is square root of n. That ensures that all the components of B, the Bi's, are, let's say, typically of order 1. In fact, this particular direction has absolutely no interest. Everything will be invariant under rotation. So I can choose all the Bi to be exactly equal to 1. This is just a particular choice. Okay. And then we draw randomly samples, which are, so we have P samples. And so each sample is a vector psi mu, where mu goes from 1 to P. And they are drawn from this distribution. So if they were totally random, and let's say with the Gaussian distribution, for instance, for each component, with the variance equal to 1 and the mean equal to 0, then you would get a Gaussian distribution for the overlap between psi mu and B, right? It would be just a Gaussian distribution. So we will bias this Gaussian distribution with an external potential, which corresponds to this particular idea of symmetry breaking along B. So the probability of psi mu will be the product of the Gaussian you would expect, which is just, so it's proportional to the exponential of minus 1 over 2 psi, sum of I psi mu squared. I mean, there is some normalization factor here, but minus V, so V is the symmetry breaking potential, psi mu dot B over square root of n. So I insist here on the scaling. I already insisted 2 weeks ago. I mean, the scaling here is square root of n. It's not n. That means it's a very weak bias. Okay. Typically, you would expect psi mu dot B to be of the order of square root of n, with this particular setting here. So it would be a random Gaussian variable. But here, this is just shifted a little bit. Okay. So we for instance, choose this potential. So there are many choices of potential you can think of. So for instance, V of this thing here, which I call lambda, so V of lambda, you can choose, for instance, exactly what I showed before. So in that case, if I have, in order to match with this problem here, this is the potential you see here. So in that case, V of lambda is simply minus S over 1 plus S lambda squared. And I'm back to the problem here. But of course, you can choose whatever you want for V of lambda. So for instance, you can choose A lambda plus B lambda squared, and you can choose even, you know, absolute value of lambda, any kind of potential you are interested in, which shows how much you are biased along some direction. In fact, the precise shape of the potential will be very important for the results. Okay. And then what we have. Okay, and then once we have that, the last point is how we infer the direction from the data. So we want to infer J, which is going to be our proxy for B that we get out of the data. And so the posterior probability for j, given all the psi mu's. So of course, all the psi mu's here are, this is the probability for one psi mu, but they are all independent from each other. Okay, so I just draw randomly p sample from this probability distribution. Then, and so this will be just by base formula, exponential minus sum of the mu, v of psi mu dot j over square root of n. And I may have some prior over j also. This is going to be important. I'll talk about that later on. But now I'm assuming some extremely simple prior, which is simply, for instance, that j, the norm of j is equal to square root of n. So it has the same norm as b, which is already some good point. But of course, this is just a base formula. I can choose another, I can do non-Bayesian inference. So in principle, I could have another potential here than the true potential with which data were generated. In particular, what people can do, and do very often, is to have some kind of inverse temperature here. That means, for instance, if beta is tend to infinity, instead of sampling from this distribution, from a posterior distribution here, what you can do is simply get the best j, the one which matches in the best way the data, okay, which minimizes this energy here. Okay. So beta equal 1 is biased, beta equal to infinity is called maximum a posteriori decoding. And so the normalization here, there is a normalization, 1 over z, and this z here is the integral over j. So I think I basically, so this is, I'm just copying the formula. And of course, if we are able to compute z, then this is the generating function for many things. If we had some sources here, so we can compute a lot of things. So this is the interesting quantity. In particular, we like to understand in the space of j's, in this n-dimensional space here, what are the j's which contributes most to this partition function. So we may imagine that in this space, which is the n-dimensional space, there will be, so this is the 0, for instance, here. There will be the right direction b, that we find if we have an infinite number of samples. But if we have finite samples, then maybe the j's, we find the best j will be somewhere here. And in fact, if we sample with beta equal 1, we'll have some clusters of points here, which are different j, j1, j2, j3, and so on, that we can sample from this posterior distribution. So there are two other parameters which are important. One is how is the precision, how big is this thing here? And that corresponds to one other parameter, which is q, the Edwards-Anderson other parameter. Okay, so in the replica approach, this is, I'm just saying, this I already defined last week, so I'm going fast here, okay. This is just, when I use replicas, this is just the overlap between different replicas, which are sampled from this posterior distribution. And we have another overlap, which is very important, which is how far away is this space here from the true B. So that's another overlap, R, which is going to be one over n, sum over I, JIA, BI. Okay? So of course, what we would have to have is R as close to 1 as possible, and we would expect that as the number of samples, P is getting large compared to N, for instance, or some fraction of N. Okay? So I explained last week how to do the calculations. I will just go to the final expression for the partition function. I explained how to introduce these other parameters, okay, how to do the integrals and so on. It's okay, you remember? Yes. So let me show you the results. So we use the replicas to average over the samples and to get the log of a partition function. So the final expression here will be that the average value of log z, which is this z here, so this is average over the samples here, then this thing is actually, there is 1 over n. So this is when n goes to infinity. So the limit of this, I should write maybe more carefully. This is to be an exponent over Q and R here of some function of GQR. So here, everything I'm going to say is in the actually was derived in the case of replica symmetric assumption. So this QAB is equal to a single Q. This thing is equal to a single R. So the stability of a replica symmetric ansatz can be tested. I don't want to go into details here. And depending on temperature beta, it's fine or not. So let's, and this has some rather simple expression. This is, I'm giving you the expression. So let me see. So we have a Gaussian integral over t, which is bypassed by this potential v of t. Okay, so I'm almost done. Okay, so let me explain everything. So here this is normalized by the same thing. So we have an integral over dt prime of the same form, square minus v of t prime. And I have two more things to explain. So what is alpha? So alpha is actually the ratio p over n. So this is the notation that people use in statistical mechanics. So this is exactly 1 over r, where r is this noise to signal ratio that people use in random matrix theory. Okay, so this is exactly what I defined before. And what is sigma here? So sigma here is just a linear combination of the different integration variable here. So sigma is equal to RT plus square root of Q minus R squared Z plus square root of 1 minus Q tau. Okay, so we have this, so this is of G, and G is given by this thing, okay? So again, you see that you find twice V. This is the V used for generating the patterns, generating the samples. And the other one here is the beta V, which is used for the inference. So we see twice at different places, okay? That correspond to the two steps in the definition of the problem. Okay? So of course, this has to be solved. So you have to find the value of Q and R for different alpha, and depending on the particular beta and V and so on. So there is a big variety of let's say, behaviors you can find, but let me tell you what are the two generic behaviors. Okay. And of course, you can do that in practice for the particular application you are interested in. So what are the two main scenarios? So there is one generic scenario. And this generic scenario is actually quite simple. And I will plot the overlaps Q and R as a function of alpha. So alpha is the number of samples per dimension. Okay? So this is alpha here. So as I go right, I have more and more data. So I would expect better and better performances. And here this is 1 and 0. So the generic situation is that R is going to increase as alpha increases, which is not very surprising. Now you have different behaviors here which are interesting. So, so this is R. So at the beginning you will have an increase which is some power of alpha. And this particular exponent here, whether it's 1 or it's different from 1, or maybe sometimes it's smaller than 1, depends a lot on the potential V. The interesting thing here is how you reach 1. This behavior is going to be 1 minus some constant over alpha. And the constant will depend, for instance, given V, it will depend on beta. Okay, whether you do at beta equal 1 or beta equal to infinity and so on. But generally, the asymptotic approach is in 1 over alpha. It's an algebraic approach. Then this is R. If you look at Q, what is going to happen is generally something steeper when we have something like that. So Q goes to 1 faster than R, which means in this geometrical image I gave, that you have B here and you have a cloud of J, so this cloud will shrink and then will be brought as you increase P towards B. So this is generically what is found. Actually, this is not totally true. There may be also some first order phase transition. And that depends a lot on the shape of V. So for instance, when V is simple as a quadratic potential, as in that particular case, this is something like that you will get. But if V can have a more complex shape, there might be some first order jumps. So at some point there will be, for instance, something like that. Okay, at a particular ratio, which depends, and this depends on a lot on the details of V. Okay. Okay, so this is the typical scenario. But there is one case which is interesting, and this case corresponds exactly to that particular case. Yes.
Can you have the second order phase transition, meaning that you make 0?
Yes, this is what I'm going to talk about. So this is the interesting case. So this is the case that you find generically when the average value of lambda is actually equal to 0. So what I mean by that is lambda bar, which is the integral of a lambda of exponential minus lambda squared to minus v of lambda, is going to be different from 0. And generically, this is what you get, right? But there are cases where actually this thing is equal to 0. So when lambda bar is equal to 0, this is not the scenario. And in fact, this is an interesting case because this is the case that corresponds to this specific application, important application, where v of lambda, remember, that was minus s over 1 plus s lambda squared. Sorry, forgot the lambda. I apologize. Okay? So when v of lambda is an even function of lambda, obviously you get 0, right? And in this particular application, this is what you get. So what happens in that case? So in that case, you get a second order phase transition. So let me draw again R as a function of alpha. This is 1. And what you get in that case is simply something like that. This is 0 up to some finite critical alpha, alpha c. And then the thing will increase. R will increase. Okay? So this phenomenon is very interesting, and that corresponds to the phase transition I was telling you about 2 weeks ago, and I'll just briefly remind you about. So here this thing means that was called, in fact, retarded learning in the paper by Nadal and Watkin, 94. That means that you need a number of samples of the order of n in order to be able to guess anything about the true direction. Okay? While here learning was immediate. As soon as you have a little bit of samples, you start to be aligned along V. So what is the intuition behind retarded learning? Well, you can guess what is going to happen a little bit. If the average value of b dot psi mu, so average over mu, is different from 0, that corresponds to this particular condition here, then that means that you have a specific direction b in the space. And when you draw the samples are somewhat aligned along this direction. This is psi1, psi2, and so on, okay? All your samples that you get from the data. That means, for instance, a very simple inference rule, like taking the sum of a mu psi mu, this is actually going to tell you immediately something about B. This is a line along B, right? I mean, the dot product is not going to vanish in the large n limit. So that means as soon as you get a little bit of samples, you have some information about B. And that corresponds to this particular case. Now, if B dot psi is equal to 0, this is a much tougher problem. That means that you have B like that, and now there is no way you can guess from a small number of samples the direction of B. Okay? In fact, you need more samples to realize that the B are biased along some direction here, but the orientation has no meaning. So what happens in that particular case is that as you move away from B, if we think in terms of the partition function over the j vectors, okay, So as you move away from, okay, so maybe I should, yeah, so the fact is that the, you can see from the equation that the entropy of the j vectors will decrease. So as you, so suppose you have some direction B here, and you ask what is the entropy of the j vectors as a function of the overlap R with the direction B. So this entropy is maximal when R is equal to 0, because this is where you have, you have no constraint over J. As you increase R, you can see that the entropy will decrease quadratically with R, at least for small r. Okay? While the gain in energy, so the way the energy will decrease, that is the way the J will align along the psi mu and so on, that will increase. So minus the energy will increase also quadratically with R. So you see, so it's a fight between two curvatures. So as long as the loss in entropy as R moves away from 0 is larger than the gain in minus the energy, then there is nothing you can do, and you are in this situation. When the two curvature becomes equal, then you get this phase transition. And the curvature of the energy is actually driven by alpha. It's proportional to alpha. Okay, is it more or less clear? Okay, so Riemann and Van den Broek applied their formalism, exactly the formulas I've shown before, to this particular case, and they found the retarded phase transition I've shown here. They had this, okay? So sorry. Exactly these formulas. But of course, you can look at the paper if you have more things. So how can we do better than that? Is it possible if we are in this regime when, let's say, there is not enough samples compared to the strength of the signal to find the direction, can we still find the direction in some way? So this is a problem which has been of interest to many people in the recent years. And the idea is that the phase transition can be actually, this ratio can be actually overcome if we have some prior information about the direction. We know something about the direction a priori without even looking at the data. So I would like to talk about that now, and this is going to be the beginning of a second lecture, so something new compared to last time. But before I do that, and I go also through the other points I would like to mention today, so some application of PCA to memory consolidation, so to real biology. And I'll talk about autoencoders also in the next, after the break. I would like just to briefly ask whether you've thought about the exercise I gave you last week or 2 weeks ago. Has anybody thought about it? It was not a very popular exercise. But it's a very simple one, actually. So remember what we did 2 weeks ago? We thought about, I mentioned to you something which is very important, and which is going to drive also the second part of the lecture today, which is Hebbian learning. How you can learn a top component of a covariance matrix with very simple neural architecture with a lot of inputs on a single output, which is a linear output. And we had a learning rule where the weight vector connecting the inputs to the output, so the output is simply w.x, where x is the vector of inputs. The learning rule is how you update the weight vector from time t to time t plus 1. That was given by something like wt plus 1 is equal to wt plus, was the plus, the product of the output times the input. And there was some normalization. Remember that? And we showed that this thing actually converges, the weight vector converges towards the top component if you iterate this dynamics for a long time and you present more and more inputs. Okay? Ask the question, what happens if you have a minus instead of a plus? That's called anti-hebbian learning. So you have not thought about it? Okay, so that's going to be important for the rest of the lecture. I'll talk about that later on. But just as a solution to the exercise in a couple of lines, if you have this anti-hebbian learning, you can see immediately what is going to happen. Compute, for instance, the square norm of the weights. Wt plus 1 squared, this is Wt squared minus 2 eta Yt squared, plus some terms of the order of eta squared. So let's forget about that if the learning rate is small. So you see that the norm is actually decreasing. And of course, it cannot decrease forever. So the only way that can stop at some point is that y of t should go to 0. That means the output is going to be 0. So that means that W is basically getting into the kernel of the covariance matrix. Okay? So there are two possibilities. Either the kernel is actually just the 0 vector. In that case, the only solution to this equation here will be that Wt will go to 0. So all the weight will vanish. Or maybe you have a covariance matrix with a non-zero kernel, okay, finite dimensional kernel. So in that case, W will live in this finite dimensional kernel, and it will be somewhere depending on initial condition. So it's a way to span the kernel of a covariance matrix. So that's something which has a lot of interest in computational neuroscience. I will show you some application. That's called lateral inhibition. That's at the basis of the lateral inhibition phenomenon I'm going to talk about after the break. Okay. Okay, so just to finish the story about the statistical mechanics framework, let me go back to the original problem of finding the top component, or let's say of inferring one particular direction, which is this specific problem here in the specific case of v lambda equal to lambda squared or minus lambda squared. So essentially what we had to do is to maximize this quadratic form here, to find the E which maximizes the quadratic form where C is the empirical covariance matrix. But now assume that we know something about the direction E. So we have some prior information, and there are many ways of thinking about prior information. One way to think about it is that we know something about the components of E. This is one particular case. So for instance, we know that the distribution of the components is going to be this one. For instance, each component E of I is going to have a prior distribution, which is given by a potential U. So this particular formulation is interesting, and I want to show you just a few examples of U which were considered in literature. So one example is U equal to infinity when the argument is negative, and equal to 0 if the argument is positive. So what does that mean? That you know that all the components of the direction you would like to find are positive. Okay? So that's a very important information, prior information. And the question is how to find a vector E which maximizes this thing under the constraint that all the components should be positive. So this is, at first sight, it seems actually a simple problem, right? Because if you choose E equal to 1, 1, 1, 1, 1, properly normalized by 1 over square root of n, and then you compute the dot product with the true E, okay? So if I even don't look at the data, and this is my guess for the true direction, the dot product will be positive with the true E, if I know that all the components of the true E are positive, right? But actually this is not true when n goes to infinity if the true vector is actually extremely sparse. You see, because if my assumption for the direction E so there is a true direction E, and I know which is E1, E2, and so on, and I know that they're all positive, and so on, okay? So a guess for a vector which is a line, or at least has a dot product positive with E, or non-zero with E, so my guess would be, for instance, 1 over square root of n times 1, 1, 1. And of course, this will have a positive dot product if n is finite, but when n goes to 0, there is no, n goes to infinity, there is no guarantee that the dot product will remain finite if E is very sparse. So suppose, for instance, this is my vector E here, then of course the dot product will vanish when n goes to infinity. Okay, so the problem doesn't look as trivial as it is not as trivial as it looks. Okay, so what Montanari and Richard were able to show a couple of 4 years ago is that actually you can investigate this problem here and find that with the help of the prior information, that is, you know that all the EIs are positive, the phase transition between telling you where you can decode and find a vector with the dot product which is guaranteed to be always finite when n goes to infinity is not r equal to s squared, as it is without prior information, it's r equal to 2s squared. Okay, so that means you need half the number of samples you would need if you knew nothing about the fact that all the components are positive. So that helps. Okay, so that it decreases by factor 2 the number of samples needed. So of course you can do other potential. You can have potential, for instance, like favoring sparse components. And one example we were interested in is a potential like this. This is sorry, this is U. This is not V. This potential is the potential which favors large components. So I will show you in the next lectures why we were interested in this potential, but let's forget about that. So what that means here is that there is a biological motivation for that, but I won't talk about it now. So here what it means is simply that we have a prior information which favors large components. It doesn't tell you that a large number of components should be 0. They can be actually very small. It doesn't matter because this potential is very flat here. So that does not contribute to the prior information, essentially. But, I mean, here, if a few components among the n components are very large, this will have a large prior probability. So anyway, for any kind of potential, what you can do is redo exactly the kind of statistical mechanics framework I've shown on the blackboard 2 weeks ago and today. And what you would like to do is now to analyze this kind of posterior distribution over the components you would like to find. The data are here inside. EI is what I call J on the blackboard before, and you would like to, let's say, for instance, sample from this posterior distribution, where now you have a non-trivial prior potential. But all the calculations I've shown can be redone. Okay? So what I've shown was in a more general case where we had a V here, a potential V, but there was no prior information, but you can combine both V and U. So here it's a case where V is just lambda squared and U is a non-trivial thing. So I won't go through the calculation because this is always the same kind of replica calculation. You can absolutely redo all the calculation. It's an exercise. And just to show an application. So this is an application in this particular case where you have here R. So this is, remember what R is? This is the ratio between the dimension of the space and the number of samples. So going to the left means having more and more samples, and here less and less samples. So S here is fixed. So the strength of the signal is fixed. This is 0.5. Okay, so this is the, so that means the top eigenvalue of this covariance metric is 1.5. And here I plot U0, which is the strength of the prior. So for U0 equal to 0, we are confined to this axis here. And this is exactly the situation where you have no prior information. So you know that if R is smaller than S squared, which is 0.25, then decoding is possible. You have enough samples to find a vector which is more or less aligned along the true direction. And if you are above, you cannot do that. Okay? Now what happens if U0 is different from 0? So we fix, for instance, R equal 1. So it's a situation where without prior information you cannot do anything. And you find two critical lines. So one line, if U0 is too small, we are asking the situation where U0 is equal to 0. The prior information doesn't help. And then if you are above this first line in this tiny region here, so if U0 is strong but not too strong, so in this tiny region, then the prior helps. That means that you find a vector which actually has a dot product positive with the true E, which is very nice. But what is bad is that if you cross again this line here, then your prior is too strong. What is going to happen is that you find a vector which actually has a lot of very large components here, because you really want to above the prior, but they are not aligned along the right direction. Okay, so that means that the prior may help only in a very tiny region here. Okay, is it clear? So that means it's just a caveat that prior information can be very good if you really know that the vector you are looking for has this particular structure. And the strength of the prior must be really fine-tuned in this particular case. Otherwise, you'll find a vector which looks like what the prior tells you should find, okay, you should look for, but which is localized in a direction which has nothing to do with the true direction. Simply because, by chance, some components of the matrix were very strong along these particular few components, and the vector will align along them. Okay?
But that, can I have a question?
Yeah.
Isn't that caveat somehow the caveat of the map inference if you were doing the marginalization and you were actually learning that strength of the prior, then you would always be able to get to that little region where the prior.
So you want to tune U0?
Right, with like expectation and stuff.
That could be possible. I don't know. Yes, in this particular case. Here it's just, I'm not tuning anything. I'm not learning anything, okay, about U0, the strength of prior. I agree. But you have a specific way of doing that in mind, or?
Yes.
Yeah, okay. Yeah, I mean, you can, of course, I mean, the partition function depends on U0. So in principle, you can optimize that over U0, which is a way of learning. So it might.
That's exactly what the expectation maximization
Yes.
is, maximizing the partition.
Yes. So that may help a lot. I don't know whether it works in this particular case. It would be interesting to do that. Yeah. Okay, so what I would like to do now, before we do the break, is to show an application of these techniques to real data. And since we are talking about neural networks, I think it's good to talk about real neural networks. So I would like to show some application of principal component analysis or bias principal component analysis to memory consolidation. So I don't know if you are familiar with this particular problem, memory consolidation, but I will just briefly tell you what it is. So it's a very important problem, which is how the memories we acquire, or that let's say animals acquire generally, during the day are transferred to let's say deep or high cortical regions during the sleep to be memorized on the long term. So there are different regions in the brain which are responsible for different way of memorizing information. So there are short-term memories, and one very important region to do that is the hippocampus. So I'll talk again about the hippocampus in the next lecture, or maybe next lecture. And the hippocampus is a very plastic region, which is able to learn a lot, but which is used as a hub for new memories. But these new memories are transferred to long-term memories during the sleep. Actually, this is what the memory consolidation theory is about, okay? Which are other cortical regions. So one very important cortical region where these long-term memories are stored is the prefrontal cortex, which is a region, so prefrontal, okay, which is a region very important for a lot of also tasks, also decision-making, task planning on many things. So the experiments I'm going to tell you about was realized by in the group of Francesco Battaglia at the Collège de France some years ago. And these are the papers. If you are interested, you can look at this paper, which is less technical than this one, but there are more actually what I'm going to tell you about is reported in this more technical paper. So what they did, they recorded the activity of about a few tens of cells, about 37 cells, depending on the sessions, in the prefrontal cortex with multi-electrode which are implanted in the brain. So they had so there are a lot of pre-processing of data I don't want to get into, how you get the activities of these cells, but let's say you have 37 cells which are recorded. And they can record the activity when the rat is actually performing some task and when the rat is sleeping. So what are the tasks? So the task is the following. So the rat is moving in a maze, which is a Y-shaped maze. So there is one starting point here. Maybe I can draw that again. So this is the Y shape. Okay. So the rat starts here. This is the starting point. And then it has to learn a rule. So the rule can be, for instance, go to the left arm. That means if a rat goes left and reaches this point, it will be given some food. If it goes right, it will be given nothing, no reward. Okay? So as you start with the rat here, it will take some trials before the rat understands that it has to go left. Right? So what you can measure is the success rate of the rat. Okay? So among the T trials, what is the fraction of trials where the rat went left? And when this success rate is becoming high, let's say about, I don't remember precisely in the paper, I think 85 or 90%, what is going to happen is that the people doing the experiment change the rule. So another rule is that you put the food on the right arm, but that would be too easy. The rat would understand immediately. So they have the rules where, for instance, you have a light here, okay, and the light is on here, and the rat has to understand he has to go where the light is on. Sometimes the rule can be also that the rat has to understand he has to go where the light is off. There is no light. Okay? So as soon as the success rate is above some threshold, then change the rule. That means the rat is constantly learning new rules. So it cannot reactivate, past memories and so on. Okay? It has to understand the new rule. And the transition from one rule to another is purely random as soon as the success rate is above some threshold. So that's the situation. So the rat is doing this task. And the activity in the prefrontal cortex was recorded in the sleep period before the task was learned, or was carried out, during the performance of the task, and also in the sleep period after the task. So you have the activity in the sleep, before, after, and you add during when the rat is learning. Okay, so these are the data. So just to give you an idea of, so there are about 10 minutes of recording in each period, so it's about half an hour. Okay, and this is done every day. So the point is that the electrodes are implanted in the prefrontal cortex and they move. It's very hard to have a huge stability. But since the time elapsed between these three different phases here is small, they basically don't move so much, so that really they pick up the same neurons. This is checked. But the day after, actually, the neurons, that can change a lot. So it depends on the particular device. But okay. So during one day you had this, and then this is repeated for many days, and then there were experiments on many different rats. So many different rats, meaning 5 rats, which is already a lot. And actually, just for a funny thing, only one rat was able to understand the rule where it has to go where the light is off. That's a tough one. Okay, so now it's the thing. If you look at the activity during the sleep before and the sleep after the task, they are very similar statistically. Okay, so I can show you. But there are some tiny differences. And the question is whether you can relate these tiny differences to what is going on during the task. The question is whether the activity in the sleep period after the task is somewhat richer and reflecting what was going on during the task. That would be a trace of memory consolidation. So the story is a little bit more complicated than that, is that the theory, which was mostly built by Georgi Budzaki over the 1890s and so on, of memory consolidation, is that actually this, and this is well established on many different aspects, is that this memory consolidation is taking place during some very specific periods, very specific phases of sleep, which is actually corresponding to the presence of what people call, so it's a period of sleep which is called slow wave sleep. It's a V here, slow wave sleep. And specifically during the presence of very strong excitation of the hippocampus, which are called sharp waves. So sharp waves are period, about a few 200 or 200, let's say 300 milliseconds, where the activity of the hippocampus is very intense, with very strong oscillation. So sharp waves. So it's short in time, but very high frequency. Okay. And during these sharp waves, it's believed that the activity is actually, the sharp wave enables the transfer of information to the PFC, to the prefrontal cortex. Okay. That's the theory. Okay, so how do these people check that? So what they did was, in the first simplest setting I'm going to tell you about, is just principal component analysis, so very simple thing. So here's typically the data you have during, for instance, the task. So the data come under the form of a raster plot. This is time. And here you have an index I, which corresponds to the index of a neuron. And you have a dot each time the neuron emitted a spike, an action potential. Okay, so the neuron was very active for, let's say, about 1 millisecond, and then it becomes silent again. So neuron number, this is maybe 3 or 4 here, is going to be active at this particular times. This one is much more active. Other ones are silent. So, but we know they are there because they might be active during the sleep phase, for instance. Okay. So this is the data. So first thing to do is to compute some kind of covariance matrix, and that can be done very easily. So you can compute, for instance, the average value of the activity. So for instance, you can binarize or discretize time, okay, in small time means. The length of the time mean, the duration here is chosen so that the correlation between the activity vectors in 2 different time means is small. That's typically a few tenths of milliseconds. And now in one time mean, each vector, each neurons will be associated a variable, which is 0 if the neuron was silent, or 1 if it was active. Okay? So you get a binary string. So you get binary configurations. Okay. And now forget about time. And what you can do is compute the average value of these activities here. So SI tau is 1 if neuron I is active in time mean tau, 0 otherwise. You can compute the frequency of activation. You can compute the joint frequency, and then the correlation matrix, which is a covariance matrix which is normalized so that each variance of the variables is equal to unity. Is it clear about the data analysis? Okay, so this is exactly the kind of empirical covariance matrix that I talked about before. So what you can do is compare actually the spectrum of this covariance matrix to what you would expect if there were absolutely no signal. If it were purely random, in the control, the null model we had, we should get the Marchenko pass-through spectrum. So you can compare, and what you see here, that's the eigenvalues, which are ranked from the top one to the last one. Okay. What you can see is that the Marchenko pass-through spectrum is here. This is along the lambda axis here. There are a few eigenvalues which come out from the spectrum. They are clearly bigger than what you would expect for the top one, which is 1 plus square root of r squared, where r is here. So here you have to be careful. What is r? N is this is not infinity. N is 34, 37, I don't remember. And p, the number of samples that we assume to be independent, so my approximation, is the number of time beans. So you can do this number, that is 10 minutes, divided by 100 milliseconds. So typically you have, let's say, 10,000 or something like that, or depending on how you choose the duration of timing. Okay? So you see a few eigenvalues, so you can do PCA in this low-dimensional space, right? So this is what they did. So they extracted, for instance, the top component, this one, and it's then you get along. Then you can project the activity along this one-dimensional axis. So it's a way to go from high dimension 37 to 1. Okay, so what you can do, and this is what they did, is to extract the top component when the rat was actually performing the task. So this is a proxy for, let's say, the collective modes which are co-activated or which are evoked when the rat is learning. And now you ask how this collective mode is actually evoked in the sleep phase. You would expect that it's totally orthogonal to the activity during the sleep phase prior to the learning, because they should be, okay? And maybe it's not orthogonal to what is going on during the sleep phase after. And here are the results. So what you see here is what they call reactivation strength, which is actually the dot product between the top component of the correlation matrix during the task with the activity at time t, or let's say in time being tau, during the sleep. This is the sleep before learning and the sleep after learning. And this is just the dot product squared. Oh, no, this is the this is just the dot product, sorry. This is the dot product. Okay, so what you see is that you get some kind of, let's say, essentially 0 with some fluctuation. And the gray areas here are the particular phases of a sleep what correspond to the slow wave sleep, okay? So where there are a lot of sharp weight. And what you see is that there is no difference in the statistical difference in the value of this projection outside and inside the gray region. While if you do exactly the same analysis with the post-sleep period, you see a completely different pattern with a very strong reactivation, actually, during the gray phases compared to the white one. That means that these collective modes, which represent some kind, of low-dimensional projection of the activity during the task performance, is actually found back in the PFC, in the prefrontal cortex, during this particular sleep period. Okay? So this is some kind of proof, if you want, or let's say actually it agrees with the theory of memory consolidation, that the activity is revoked, and the idea is that the kind of Hebbian learning I was talking about 2 weeks ago is actually taking place there, and is that it will strengthen the connection between the neurons in the PFC in order to stabilize these memories. So just to be more precise, you have the PFC here, prefrontal cortex, and you have the neurons here, and you have the hippocampus. So when the task is learned, since this region is extremely plastic, there is some learning mechanism which will create, that's a theory, some connection between these neurons, which will stabilize some patterns of activity. Okay? Obviously, when the rat is learning, this region is also communicating with PFC, right? So you will see some activity here, which is actually induced by the activity here. And this is exactly what is measured with the PCA. When you do PCA and you find a vector, you find some collective mode here. That's the task phase, okay? Now, during the sleep, the idea is that there is a very strong communication in this direction during these particular slow wave sleep periods here, and that the neurons here are driven by the hippocampus. And if learning takes place, then it will strengthen connection here in order to stabilize the patterns of activity which are present in the hippocampus. So that in the next day and so on, then this thing will go into a different subset of population or in a different way, but the connection will be stabilized and the memory is recorded. Okay. So that was the application of PCA I wanted to show because I think it's a very nice one. It's much nicer than doing PCA on MNIST. And it's very interesting. But I'll come back to this data in a very, a different setting in the next lecture. Yeah.
The first part of the talk, I mean, could it be that since you were telling us about this potential V and the prior, that taking those into account could actually improve this analysis even more, or like fine-tuning, not doing just the plain PCA?
Yes. So here actually, okay, I have to say the truth because you asked me a question. Okay, they did 97 sessions.
97.
Sessions. They had 97 days. The number of days times the number of rats, total number of days, okay? It was not the same rat for 97 days. The session which is reported here, that's the best one, where you see very clearly the signal, okay? So for this particular session, I think you don't need anything to see a very strong signal. But your point is right. For many other sessions, for some session you see something similar but less nice, okay? And other session you see basically nothing. So the question is whether other potential could help. So what I will show, not today but another day, is that actually if we do a better analysis where we consider the discrete character of these variables, they are not considered as Gaussian variables and so on, you can do a better analysis in the sense that you see more sessions coming out of the noise. Okay? But you are right. What I showed here was just very simple PCA that was done by these people, and they reported this analysis. But I will tell you next time another story. I mean, this is typical of people doing experiments. In this particular field, they have sometimes some kind of crude statistical analysis techniques, statistical techniques, and instead of improving the statistical techniques, sometimes they just do other experiments if they don't see any signal. I will show you an example of that, which is actually quite funny. And if you improve the statistical analysis, you can get the signal. I'll show an example in the hippocampus, which is very, very clear. Maybe,
Just a naive question. Sorry, it's a bit silly. Does it mean that the rat is dreaming during these phases and redoing what he did during the day, or it has nothing to do with that?
No, I mean, you may want to call it this way. Yes. Essentially revocating, retracing. Yes. But actually that happens, this kind of sharp waves, that's an important thing to understand. This kind of sharp wave also takes place during the awake period, when the task is performed, when the rat is immobile. And I will show you an example of that. In the hippocampus, you can see traces of reevocation of what the rat has done in the previous trials, in particular for the trials which were successful. So when the rat is planning, actually it's just revocating these things and just follow the right path. So this is not only during sleep, but also during awake period when the rat is thinking. Yes, definitely. So these sharp waves are also present in primates, so in humans, probably the same mechanism. While other things which are specific to rodents are not present in humans. Like I talk about that. So maybe we can do a break. And
okay, so let's have a 10 minutes break.
some yes, I would like to because I have a number of courses that I have to follow through the college round.
So we deal with that in the later
Quindi fai
Okay, fine.
At some point I will ask people to send me an email
prende
Okay.
non linearmente
Yes.
e poi dopo
Yes, because last time we spoke here, that is fine.
c'hai un I qui, poi c'hai IJK